Hiya 12s, this is Mr. Lim again. This is the second video on amino acids about the zwitterion nature and their amphoteric nature of amino acids. Right. So, we're going to be learning about amino acids, duh. Alright, so amino acids can accept and donate protons from the amine and carboxylic acid groups respectively. So we've already established that the amine group and the carboxylic acid group both exist on an amino acid. Alright. And so therefore, since amines have the ability to accept protons, okay, so, oops, that doesn't look like a very good line. They have the ability to accept protons, okay, so that can turn into an NH3 plus, and the carboxylic acid can lose electrons, okay, oops, that's a terrible diagram, okay. Not lose electrons, lose protons. Okay, so you lose that hydrogen there, and this becomes a negative charge. All right. So because that they can donate and accept protons, they have the amphiprotic nature. All right. So let's show the hydrolysis to accept and donate a proton. Okay. So let's say we are going to deal with the. Let's just draw a general one. H2N CH with an R group, COOH plus H2O. Okay, now this is not taking into account the R group because the R group can do different things. Okay, let's say it's donating a proton, it's going to turn into H2NCH with the R group, COO minus plus H3O plus. Okay, so that's it, donating a proton from that proton, in fact, from the carboxylic acid group and onto the water. Okay, but you can also have the amine accept a proton. Okay, so here's that exact same amino acid. Okay, and it's going to accept a proton, and whoops, that's not going to form H3O plus, it's going to form OH minus. Okay, so what you can see there is that the hydrogen, there's an extra one here. All right, and also notice where I put the charges. You place the charges wherever the actual charge is, okay, because that's kind of something that we'll talk about later when we go to zwitterions. The charge must be shown wherever the actual charge is. Okay, so that's the way that this amino acid can donate and accept protons. Okay, so they'll accept or donate protons depending on the conditions that they are found in. Okay, so in neutral conditions, amino acids will donate and accept a proton, so they'll do both, which effectively means that they've actually have net gain or loss of 0 protons because you've donated one and accepted one, so that it becomes a zwitterion, which means it has two charges on the same particle. Okay, so what does that mean? Here's my particle with my carboxylic acid on one end and my amine on the other end, and my R group over here and an extra H there just to make sure that it's right. Okay, so it's going to become a zwitterion, which means that it's going to gain an extra hydrogen here, making it a positive charge on that end, and it's going to lose that hydrogen there with that negative charge there. All right, so that's the zwitterion form with the two charges on the same particle. So that's all one particle, but it has a positive end and a negative end. All right, so the same particle can have a positive and negative end. That's the definition of a zwitterion. Okay, and there's your zwitterion form of an amino acid. All right, so in acidic conditions, and remember, whenever you're asked to explain about acidic conditions, you have to talk about the hydronium ions being greater than the hydroxide ions. Okay, so remember, this is no longer year 11 where we just say acidic is below pH 7 or something. We need to say that, okay, acidic is where there's more hydronium ions than hydroxide ions. Okay, so when you've got lots of hydronium ions around, the amino acid is going to accept hydrogens from those hydronium ions. Okay, so you're going to end up with OOH, don't forget that extra H and the R group, and then the H2N. Okay, there's your amino acid. However, you should recognize that it's in zwitterion form, so you need to be showing, because it'll be starting from a neutral thing, it's going to be in its zwitterion form. Okay, so that's how amino acids look like normally, and then you add it to a hydronium ion. So your hydronium ion, H3O plus, okay, so this zwitterion is going to accept one of the protons and leave water at the end. Okay, so what is that zwitterion going to look like? Here's the center carbon, here's your H and your R group. It's going to accept a hydrogen. Where is it going to do so? It's going to accept it on the carboxylic acid end, and the NH3 positive end is still unaffected. All right, so you'll notice that this now only has one charge on it. Now it's positively charged, and therefore it's no longer a zwitterion, it's just an ion, right? And so that's the positive ion of an amino acid. All right, and then you've got, because it's taken away from the hydronium ions, the extra hydrogen. All right, so this is often a very common question in exams, where they're just going to say, draw this in acidic conditions, or draw that in basic conditions. So you're going to need to recognize, okay, in acidic conditions, lots of hydrogens around, it's going to accept those hydrogens and have more hydrogens, not less. Okay, don't just think of acid, okay, that means I have to make the amino acid donate. No, it's in acidic conditions, so therefore it's going to probably accept protons. Okay, it's very easy to get those confused. Okay, what's it going to look like when hydroxide in basic conditions? So let's draw that out. Here you have your zwitterion form. Don't forget the H and the R group, and you add in a whole bunch of OH minuses. Okay, and you're going to therefore donate protons to this hydroxide ion. And where does those ions come from? Where do those hydrogens come from? That amine group. Okay, so that amine group loses a hydrogen, and the rest of it stays the same. And you have a water as well somewhere kicking around. Okay, so this hydrogen here on the amine group has come off and gone to the water over there, right? And therefore you've ended up with a negatively charged amino acid, because it has donated its protons to the hydroxide ions, so therefore it is no longer a zwitterion, is now just a negatively charged amino acid. So remember, when you put an amino acid into acidic and basic conditions, it's going to act like the opposite. Okay, it's going to act, if you put in basic conditions, it's going to donate protons, because it's going to have a whole bunch of hydroxide around it, and vice versa for the acidic conditions. Very common to get it wrong, and if you get it wrong, sucks to be you. All right, adios.